Okay, so we're going to do now question 3 in chapter 6, sp3, page 122. And what we have is a slingshot. Slingshot is pretty much like a Y stick. You hold it here, and to these two ends you attach an elastic band. And in an elastic band you can put a little pouch that can hold a rock. The idea is you pull back on the rock, which stretches the elastic and gives the system potential energy. If you then let go, when the elastic is stretched, the pouch and rock will shoot forward and the rock will go far, depending on how far back you stretch the elastic. The formula for a system like this with something that stretches can be thought of as a spring. We've studied springs and we know the force due to a spring. It has the formula F is equal to minus kx, where k is something called the spring constant. The potential energy of a stretched spring or compressed spring is equal to 1/2 kx squared. Again, the k is the spring constant or Hooke's constant, and x is the distance from equilibrium. In this case, it's squared. For the force, it's not squared. So the author gave us the equivalent spring constant, 600 newtons per meter. Newtons per meter. Remember, work is newtons times meter. K is newtons per meter. So let's see what it says. A slingshot consisting of a rubber strap attached to a Y-shaped frame with a small pouch at the center of the strap to hold a small rock or other projectile. If you're unfamiliar with slingshots, maybe you should see David and Goliath in the Bible. The rubber strap behaves much like a spring. So we're going to suppose that for this slingshot, the spring constant is equal to 600 newtons per meter. So this is something that's given in the problem. The author gave us that. And then that we're going to pull back the strap approximately 40 centimeters or 0.4 meters. Then you're going to release it. Question A says, what is the potential energy of the system prior to release? What is the potential energy stored in this system once you stretch the spring 0.4 meters? Well, the formula for potential energy of a spring is 1/2 kx squared. We plug in 1/2. K, we're told, is 600. And x, we're told, is 0.4. So we multiply that out. So we have 300 times 0.4 squared equals 48. 48 joules. Part B says, so that's equal to the potential energy. That is the answer for part A. Part B, what is the maximum possible kinetic energy that can be gained by the rock after the release? Well, we know conservation of energy. Energy initial is equal to the energy final, so assuming there's no losses due to work done or friction or anything like that, the kinetic energy, all the energy initially is potential energy, and that would equal to all the energy once the rock is released. It's not touching the elastic anymore, so there'll be no more potential energy, so all the energy has to wind up being kinetic, energy of movement. So the initial energy is equal to the final kinetic energy. And the initial energy is 48, so the final kinetic energy is 48 joules. That's under best conditions with no losses. Part C, if the rock has a mass of 50 grams, so the rock has a mass of 50 grams, which is 0.050 kilograms. Remember, we have to convert to kilograms. Kilograms and meters. The rock has a mass of 50 grams. What is the maximum possible velocity after the release? Well, the maximum possible kinetic energy is 48. So kinetic energy is equal to 1/2 mv squared, but the maximum possible kinetic energy is 48, so that's equal to 1/2 mv squared, but m in this case is given to be 0.05 kilograms, and it wants to know the final speed, so we keep v as our unknown. Solving this again, one equation, one unknown. V winds up being, so what I'm doing is, hopefully you can see that, 48 times 2, going to multiply both sides by 2, and then we got to divide both sides by 0.05. That tells us what V squared is, 1920, so take the square root of that, and we get 43.8. 43.8 meters per second. And what you should always do in this class is try to imagine that 43.8. How big is it? Is it realistic? 43.8 meters per second. That is quick. That is very quick. So it's something like 50 yards about, 45 yards about. You're doing that in a second. In case of a slingshot, yes, that's very possible. D says, will the rock actually reach these maximum values of kinetic energy and velocity? Well, the answer there is quickly no, it won't. Does the rubber strap gain kinetic? Okay, so it wants to know why. So the answer is no, and the reason, why won't it? Because once you let go of the rock, you'll get some fluttering of the elastic here. The elastic strap will begin to flutter. You also have air resistance. You can hear the rock go by, so energy is lost in moving the air. So for those kinds of reasons, you have losses. So the initial kinetic energy is 48, but the final kinetic energy is not 48 because of the losses. The strap is going to take some of the energy. Air is going to take some of the energy. Sound is going to take some of the energy. Right, and that is question 3.